All right, so we are going to talk about margin of error and this new concept now that we have here, which is matched pairs. All right, so margin of error. So when we talk about margin of error, this is going to be the same for our confidence interval that we did with proportions. So remember, my full formula here is my confidence interval is my statistic plus or minus my margin of error. Okay, so our margin of error is this part of our formula, which is with means, it's going to be T star times S over N, right? So S over the square root of N. So that's what my margin of error is. So, and I have this right here. So let me write this a little bit bigger. So T star times standard deviation of the sample over my sample size. Now, when we had this with a proportion, we could find our Z star really easy because we knew that this was our confidence interval. So for example, like 95% confidence. So we could find our Z star. And then we had our proportion that we could plug in here to solve for our sample size, okay? That is not the case. So why can't we solve for N like we did for proportions? Well, we can't find T star without knowing, we have to know our degrees of freedom. So if I go here to my calculator and I go here into my distribution and I go to inverse T, so remember inverse norm is what gives me my percent confidence, my Z star. Inverse T, it asks me for my degrees of freedom. Well, remember your degrees of freedom is your sample size. So it depends on sample size. And my formula for degrees of freedom is N minus 1. So if I know my margin of error, I can't calculate T without knowing N. All right, so we don't know S since S relies on our, or so we do not know S since S relies on our sample data. If we don't know N, then we can't find our S. So we have a couple of assumptions that we're going to use for this. So when this happens, we are going to go back to Z star. So Z star is going to be an estimate for T. This only happens if we don't have a sample size. So the reason we started with Z star in the beginning of this unit is because we could still possibly use it for a mean, but only if we don't have our sample size. All right. The other fix for this is because remember we don't know S, we're going to use our value of our population standard deviation. So our margin of error to determine sample size for a confidence interval for a mean is going to be this. Our margin of error is going to be our Z star now times our population standard deviation over the square root of N. So this is what we use. Let me be really clear. This is what we use when we don't have an N to find T star. All right, so let's do an example. It says, medical researchers would like to do a large study to determine the mean cholesterol level of children aged 5 to 10. They want their estimate to be within, that's my buzzword, so within 1 milligram per deciliter. So I'm going to just go ahead and start writing down what I know. My margin of error is going to be 1 milligram per deciliter. The true value at 95% confidence. So 95% confidence interval. Let me keep reading this. Previous studies. This means that I've got data that's going to tell me what my standard deviation is. So previous studies have shown the cholesterol level in children for this age varies with a population standard deviation of 5 milligrams per deciliter. Now this one is super nice because it very clearly tells you that it's the population standard deviation. But really all we need to know here is when we see previous studies. So that means my sigma value is going to be 5 milligrams per deciliter. What is the minimum number of children the researchers need in their sample? So I'm looking for N. Okay, so I don't have what I need. So the first thing I'm going to do is I'm going to convert this to a Z star. So I'll go in here and do inverse norm, 0.95. Oops. and that gives me my value here of 1.96. So I know that my formula, margin of error, is going to be z star times sigma over the square root of n. All right, and I have everything that I need. My margin of error is 1. Now, I'm not converting this to a decimal because this is a mean. It's not a proportion. So this is 1. My z star is 1.96. My standard deviation is 5 over the square root of n. All right, so doing a little math, I'm going to divide. So I have 1 divided by 1.96. Oops. All right, so this gives me, just to show you the steps here, 0.5102 equals 5 over the square root of n. So I'm going to flip-flop these, so 5 divided by this value. So this gives me the square root of n is 9.8. And then to get this value, I square both sides. So I would have n equals 96.04. Now remember, with our samples, we always round up. So I'm going to say 97 children. Okay, let's keep going. So now we're going to deal with this concept of matched pairs procedure. So we did matched pairs when we did our unit on setting up experiments. And remember, what a matched pair was is if, for example, I had 2 twins and I want to see what happens with 2 twins. Or if I have 2 different things that are going to happen. So first I'm going to look at the effects of sleep, and then I'm going to look at the effects of an energy drink. And then here I'm going to look at the effects of an energy drink, and then I'm going to look at the effects of sleep. So we did kind of a matched pair when we're looking at both different things here that have the same general characteristics to begin with. So what is matched pair? Comparative studies are more convincing than a single sample investigation. For that reason, a one sample inference is less common than a comparative inference. If we can compare 2 things, we're going to get a better picture of what's really happening. Study designs that involve making 2 observations on the same individual. So remember here, 2 observations on the same individual, or 1 observation on each of 2 similar observations result in paired data. And that's what we're looking for. So what we have here, and I'm going to just write this. So if I have a matched pair, and this matched pair procedure that I'm going to run here with this test is going to be similar to a significance test for a mean. All right, so what do we know? This goes back. So a matched pair design is a special case of randomized block design. Using a blocking variable, subjects are arranged in pairs matched on relevant factors. So what we're looking for are 2 things that we can identify. Matched pairs may be formed naturally or by experiment. Every pair receives both treatments by randomly assigning one treatment to one member of the pair and subsequently assigning the remaining treatment to the second pair. So, for example, if I had matched pairs, I could say one gets sleep, one gets an energy drink. One gets sleep, one gets an energy drink. All right. Alternately, each subject may get both treatments like this, sleep and energy drink, then energy drink and sleep. So that the order here, again, has to be randomly assigned. So what I have here is paired data comes from measuring the same quantitative variable twice. We can find the difference between the 2 data points for each subject, and then we can analyze the differences. So we are going to use a one sample T procedure when we perform inference on the mean difference. So these methods that we have here, this method is called matched pair. So when you see something that's going to be a matched pairs design, you need to think back, okay, what I'm going to be using here is this one sample t procedure and this mean difference, and we usually see this as a mean with a little d here that's going to tell us a difference. So what does this look like? So it says inference steps will look very similar to a one sample t procedure that we've done already. So one sample t-test. So our communicate. This usually says that the difference, remember that's what we're looking for here, the mean difference, the difference is 0. Now, what we had with proportions is we said P1 equals P2. And so we said that these are equal to 0. Well, here we say that the difference is equal to 0. It doesn't have to be 0. It can be a value, but normally it's going to be 0. And then we're going to have in here just whatever our data we're going to look for. So greater than, less than, or not equal to. All right? We have the same thing going on over here with our random conditions. So given sample data, we graph for outliers. We're not checking to see if it's normal. We're looking for outliers and strong skewness. Here is my formula for my sample t-test. So it's my individual sample mean minus the difference over the standard deviation. And the p-value here, we're going to still use our t-CDF on our calculator with our degrees of freedom. So as you see, everything here is very similar to what we did. And then the same thing, because our p-value of whatever value is lower or higher than alpha, we reject or we fail to reject. So our conclusion is going to be exactly the same as what we had before. All right, so let's do one of these. It says, researchers wanted to determine if a new type of medicine will help lower glucose production in individuals with type 2 diabetes, because subjects with type 2 diabetes vary in their eating, exercise, and weight loss. Researchers decide to do a matched pairs experiment. Boom, tells us right there. For 1 week, individuals will be placed on new medicine and told to continue with their normal treatment of type 2 diabetes. Their blood sugar will then be recorded as a percent. For the next week, individuals will be placed on their current medication. This experiment will be double-blind, and the order the subjects receive the medicine will be randomized. All right? The following is a table of the results along with the difference current minus new. So what I have here is that this order, it tells us the order was randomized. So I don't know which of these happened first. All I know is that this is the difference, current minus new. So what this looks like is this is one subject. All right, so then this would be the second subject. So all of these are my subjects. Do the data suggest that there is a significant difference between the current medicine and the new medicine for lowering blood sugar? Use a 5% significance level. All right, so let's go in here and do our communicate. So is there a significant difference? Because this tells me difference, I'm going to use a mean difference. And it's going to be the mean difference, when I define this, the mean difference in blood sugar between the current minus the new medication. All right, so a couple things I want to go back and look at here. So this is saying we want a difference between the current and the new medicine. So we have current medicine and we have new medicine. This kind of looks like two samples, right? And we know it's not two samples because each subject got both samples, okay? So this is not a two-sample mean test. Super important. So you have to kind of look at this overwhelming thing here to figure out what this looks like. The other thing here is we have current minus new. All this is saying here is the following table along with the difference between current minus new. So what we want here with current minus new is we want to see if there's a significant difference. So because of that, we want this to be positive. we want there to be a difference in their blood sugar, and we want that to be positive because we want the current medicine and the new medicine, when we subtract this out, we want that value to be positive. So if I identify my null hypothesis, I'm going to say that there's no difference between the two medications. And then my alternate hypothesis is that there is a difference, and that difference is going to be positive. The other thing I know is that my alpha on this was 0.05. Okay, so I'll go in here and look at my conditions. So first thing is I have random assignment. And it tells me that up here that they're randomly assigned, double blind and randomly assigned. So I have this 10% condition, and I'm just going to put here, don't check, because it's an experiment. And then I'm going to look at my normal condition. All right, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm going to go up here and say n equals 16. So my normal condition, I have 16 is less than 30. So because 16 is less than 30, I have to graph the difference. And so I'm going to go in here and I'm going to put in the data that I have. Now, I know there's a lot of data, but really all I care about is the difference. So when I go in to stat edit, the thing that I'm going to enter is the difference. So 0.2, 0.1, negative 0.1, 0.2. Okay, let me put these in. All right, so there's all my data. So my stat plot is on, so I'm going to do zoom 9 for zoom stat. Oh, let me get rid of that line. So here's my graph. Now remember, this kind of looks like I have an outlier. So if I look at this data, I'm just going to go ahead and change this. I've got negative values in there, so I'm going to change my window from negative 0.2. Let me just make it 1, and I'm going to increase by 0.2 because I think that'll... Okay, so it kind of looks a little bit skewed, but I don't really seem to have any outliers. So I'm going to go ahead and sketch this super quick. And this first value here I have 4 of. This is my quantity, and this is my difference of current minus new. And my first bar here at 4, this happens at negative 0.2 to 0. My next one's at 3, and this is 0 to 0.2. My next one's up here at 5, and this will be at 0.4, and then I have 2 and 1, and this is 0.6 and 0.8. All right, so what I'm going to say here is there are no visual outliers. Or major skewness. Looks like maybe a little bit, but it's not significant. All right, so now let me get down here to my calc. All right, so what am I going to do? So I have matched pairs. So because I have matched pairs, I'm going to run a 1 sample t-test for means. So my t-value is x bar minus my difference, so sample minus the population, so this is my overall difference, s over the square root of n. Now, I've got all this data in my calculator already because I already listed it as list, so I'm going to go in here and do a 1 vars. And now I'm just going to pull this data right over here into my formula. So my t-value is going to be hold on. Something doesn't look right. Let me look at my data again. 2, 1, negative 1, 2, 1, 5, 3, negative missing one. That's why. Let me run it one more time. All right, so what I'm going to say here is that my t-value is 0.156. So hopefully you put the data in right. You got this right off the bat. My S sub x value is 0.263, and my n value here is 16. All right, so when I plug this in, I have 0.156 minus my value here, which is going to be 0, over 0.263 over the square root of 16. Now, I can go in and I can calculate this value, or I'm just going to go in here and I'm just going to run it. Once you've got all of your data, I can go to stat, I can go over here to test, and it tells you right here that you're running a one sample t-test for means. So here's my t-test right here. All of my data populated because I ran my 1 vars. And what I know is that I want my difference to be greater than 0, so I have to go ahead and select greater than 0, and then I'm going to calculate that. And this tells me, oh shoot, how did I do that? Hold on. There we go. This tells me that my p-value here is 0.0157. So remember, it just gives you p. My p-value is that area under the curve, 0.0157. All right, so now I'm going to look at this. It gives me a significance level of 0.05. So if I have 0.0157 and 0.05, I see that this is less than. So my conclusion is because the p-value of 0.0157 is less than 0.05, we can reject the null hypothesis. We have, and that's what it asks us up here. Does the data suggest there's a difference between this? So does the data suggest we have convincing evidence that there is a difference in the average blood sugar levels between current and new medication. All right, so here's the difference. The only reason that we really had this lesson today was to understand that we're going to get into 2 sample data, and this is not 2 sample. This is a matched pairs. So we still run a 1 sample t-test. All right, so when you see matched pairs, it's a 1 sample.